大丈夫、ごめんなさい。Okay, thank you.
For the next presentation, I would like to welcome Professor Amano himself from the Graduate School of Information Science and Technology from the University of Tokyo. And he will give a talk about the interface of the Pulp project for RISC-V core.
次は東大の天野先生からの、パルププロジェクトの、RISC-V コア向けインターフェースということで、ご説明いただきます。よろしくお願いいたします。
Thank you for your introduction. I'm very sorry to say that I made this slide in Japanese because Kawasaki-san asked me to do so. Okay, so I will do it in English, but of course, slides are all in Japanese. That's a problem. Okay, my talk is for the open source cores and interface. Well, the best benefit of RISC-V is that there are various kinds of open source, open cores are open. But of course, we need some memory or peripheral interface. That means that we need some kind of interface. Of course, there are various kinds of standard bus. For example, AXI bus, AMBER bus, or something like that. But you know, they are all some kind of complex bus. And in many cases, they are overspec. Yeah. Well, this is an example of AXI bus. Yeah. In the environment for FPGA, we can only connect these bus with some kind of line. But this one line includes those signals. It's very complicated. Well, FPGA community established a very convenient environment. So this bus is easy to be used. But in general, this kind of convenient environment is not existing. So we need some kind of IPs or some kind of sophisticated mechanism to use this kind of buses. Okay, so today I would like to introduce Pulp project. Pulp is an abbreviation of Parallel Ultra Low Power Project. This project is driven by ETH Zurich and University of Bologna. Professor Luca Benini is a leader of this project. He is now in United States and yeah, he just joined the ISSCC in the previous week. Well, you can check it with this GitHub. His project opened various kinds of open source IP related to RISC-V. And the key interface is Open Bus Interface, which I will introduce in this presentation. Most of IPs can be connected with this OIP. Well, the very interesting thing is that it uses a very sophisticated description in system Verilog. It's very smart, but somehow hard to be used. Yeah, we developed an SoC-style FPGA which uses RISC-V CPU core called SLMLET 2. I will explain the usage of this OBI by using this example. Well, this is a waveform of standard I/O open bus interface, or OBI. It's very, very simple interface. Well, it is divided into two parts, manager and subordinate. Maybe it is some kind of the master and slave, but we can't use such kind of words now. Okay, so we use manager and subordinate. Okay, so manager is represented with these blue lines. There are request, address, and W data. When request is asserted, we should post the address and W data, write data. Okay, so subordinate has to reply it by asserting this grant signal. Okay, when the subordinate wants to send that data to manager, it means that manager reads the data. In this case, this reading data is placed here, and with the R valid signal is asserted. Then the manager reply it by using R ready signal. Yeah, it's just a case of one data write or one data read. But we can send the multiple data in the continuously assert this request signal. So the rate of data transmission is not so bad. Well, this OBI is defined by system Verilog's interface description, like this. We can write interface something. In this case, interface OBI bus, and define parameters and define each signal like this. So by sharing this interface OBI bus, many IPs can use this kind of protocol very easily. Okay, the concept is described in this diagram. Well, unlike other bus, we can construct the system by using a demultiplexer, multiplexer, or switching mechanism. There is a switching box in the which provides an OBI interface. So we can build complicated system by the combination of the multiplexer, and switching system. Well, if we need to use DMA controller system, it must treat access this SRAM part. So, of course, the CPU must access this SRAM, and it must use other IOS modules. In this case, we place the multiplexer here, divide the bus, and then here, by using multiplexer, both DMAC module and CPU can access this SRAM. Okay, so this is an example of demultiplexers. Well, if you can read system Verilog, you can read this. You can maybe you're familiar to this kind of description. Well, unfortunately, most of the people now think that the system Verilog is a just simple extension of Verilog description. But recently, it's not true. Yeah. system Verilog allow this kind of sophisticated configuration parameter setting. Yeah, by changing this kind of configuration, we can use various kind of OBI package, which has different interface. And from the outside of the modules, this kind of parameters are reset. Okay, so now we, in this demultiplexer modules, we also provide clock reset and selector, which selects the demultiplexation of this module. But also, of course, we need to have subordinate interface and manager interface. Maybe only single description is desirable, but unfortunately in the world of Verilog or system Verilog, we need to specify every input and every output individually. So here we need input description, output description here, output input here. But they are for manager and they are subordinate. Okay, so when we use this demultiplexer, this kind of description is used. Well, I think some of you feels very strange to see this description. Well, yeah, this is the demultiplexer. The multiplexer has single input and multiple output, like this. Well, in this case, this is simple output, but input. But this direction, this port is subordinate port. So we have single subordinate and 4 manager port. Okay, so, but this description has only 1 manager port. But here, number of manager port is defined in here, 4. So just changing this part, we can change the number of manager port. Okay, unfortunately, now we need some kind of wrapper to use this this description. Well, yeah, this scan module is really used module in our design. It's the content of this design, but we need this kind of description to connect OBI bus. Because CADs need to be information for input and output direction of signals. So we need to separate bus and to fit the face here. Okay, so let me explain our example chip called SLMLET 2. This is an SoC style FPGA which provides a RISC-V host chip, host module, and interesting, a new FPGA cells. Okay, there is a DMAC DMA controller here, SRAM here. And we use hyperbus and bus switch here. So you know this kind of system is very complicated and we need some mechanism to coordinate these modules. Well, this is the layout of this chip. This part is for FPGA and they are ramped. The layout of RISC-V is scattered in this area. Well, let me explain the architecture of Scalable Logic Module, which is used in this SLMLET too. Yeah, this module was invented in Kumamoto University, our co-author, It uses a Shannon extension and can decrease the content of configuration memory. Well, this is the concept diagram. Well, for implementing k-input lookup tables, this SLM only needs k-1 input LUT. So order 2 power k-1. We need some input modules and output modules. And most of logic can be implemented, this simplified LUT structure. So we can reduce the configuration memory and also reduce the area of each FPGA configurable module. Well, now let me explain RISC-V core. We use the CV30E40S. It is an IP in the Pulp project. Yeah, Pulp project supports several kinds of RISC-V core, and it's a very standard one. It's very easy to understand. Yeah, the pipeline structure is very, what to say, the textbook-like, 5-stage pipeline. Instruction fetch, instruction decode, execution, and memory here, and write back stage. Yeah, the reason why memory isn't here is that the memory stage requires a specialized function to access the other or cache system. Okay, so our implementation uses AXI bus, also as well as I/O, as well as OBI bus. And we need external bus. So we also use a hyperbus system. And we need to implement cache system by ourselves. So we use the interface somehow like OBI. It's not completely the same as OpenEye. Okay, so maybe you don't know about hyperbus and hyperram. It's a very interesting bus, I think. It's a high-speed SPI, the highest version of SPI. So it is sometimes called XSPI. The benefit of this bus is that we need only standard interface buffers to provide this bus. Well, you know, if we want to use DDR4 or DDR5 DRAM, we need to provide special buffers on our chip. It needs, of course, a very expensive I/O for buffers, but it doesn't need it. And relatively good performance can be obtained. It's competitive to USB 2.0 and 1 gigabit Ethernet. And most of benefit of this hyperbus is that we can connect HyperRAM, embedded DRAM, directly. Just connecting to the bus, it works. It provides 128 megabit. Of course, it's very, very smaller compared with the recent DDR4 and 5 DRAM. But in my sense, they are overspec for most of Asia computing. So I think this RAM can cover most of IoT device. The power consumption is very, very low, 35 microwatts in the sleep power. Okay, this shows the hyperbus protocol. Unlike IOB, it focuses on the continuous or block data transfer. Okay, so this is a real diagram of our SLMLET tools. Here is RISC-V processor, and there is a DEMAX module. And we, unlike other SoC, we provide the FPGA here, SLM module. So FPGA module can access SRAM directly. So we need to this multiplexer module here, and DMAC also tries to access this DRAM for external communication by using hyperbus. And this is a scan module. It must be access. It must access this SRAM directly. So we need to build very complex data communication patterns. But by using OBI interface, we can do it relatively easily. But this connector is somehow a problem. Yeah, in the rule of OBI, we cannot connect subordinate and manager directly. So we need this kind of bus changer. Well, yeah, this chip is now under bonding. Well, we can, yeah, I think we can announce the performance and result of evaluation in this summer, hopefully. Well, this is a summary. Well, in my sense, OBI description is very interesting. It uses this very sophisticated description in system value. It's amazing. But there are some problems. We need a lot of description, a lot of sentences to use interface description or other description in system value. And the description is scattered into various kind of modules. So the readability is not so good. Yeah, I think it's the same problem when you use C++ description. Well, the definition is distributed in some modules. Okay, so the problem is that the CAD have not treat this description very well yet. For example, Synopsys Design Compiler, the newest version, 2023 December part version can treat it. But if you use older version, it's impossible. And Xilinx CAD cannot treat it at all. And on the simulator, NC Verilog is very commonly used. Cadence compiler, Verilog simulator cannot treat this description. But Exerium and Verilator can treat it. Maybe in the future, most of CAD will treat this kind of system Verilog description. Yeah, in my experience, we need a lot of time to understand this description. But maybe the debug was easier than the previous version Simulator 1, which uses the original interface. Okay, thank you very much for listening.
Thank you very much, Professor, for the talk. And do we have any question?
Yeah, yeah, I think it's okay. Yeah, thank you very much for listening it anyway. And yeah, we have long break time, right? Okay, so yeah, I think it's very good because well, the problem of this conference is that it's very pushed into, squeezed, yeah, many things into one day. Okay, so please take long break and come back 3:30. Mm. 3:30. Oh no. So,
So this is after you, and then there will